All right, so in this video, we're going to apply Gauss's law to find the electric field for a really long cylinder that has uniform density rho. Okay, so for part A, we will find the electric field for R greater than big R, and then part B, we will find electric field for R less than big R. Okay, so for part A, we need to pick a surface, and we're going to pick one that matches the symmetry of the problem. Okay, and so we will pick we'll pick a cylinder. Our Gaussian surface has to have, it can't be infinite, it can't be really long like our cylinder, it has to have defined dimensions. All right, so we're going to make it, we want to find the electric field at a point out here. So it needs to have at least that radius. Okay, but we're going to give it a defined length. Okay, so here's our Gaussian cylinder. Okay, it's going to have a length of L, and it's going to have a radius of little r. Okay, and it's completely enclosing the really long cylinder, at least a part of it. Okay. The other thing, what is the electric field doing from that charged cylinder? So it is going to be radially outward at all points, kind of like a sphere, right? Radially outward at all points, going through the wall of the cylinder. But notice that it's parallel to the edges at all points. Okay, so it's parallel to the edges. So we really have sort of a side. We have side 1, side 2, and then we have the wall of the cylinder. Okay, so applying Gauss's law, we have closed integral E dot dA equals Q enclosed over epsilon naught. Okay, so let's deal with the left side. So left side of the integral, it's not continuous, so we have to break it up. Integral through side 1, E1 dot dA, plus integral of side 2, E2 dot dA, plus the wall of the cylinder, E3 dot dA. Okay, like we said before, the electric field is going to be parallel to the sides, so the flux through the sides is 0. Okay, and so we just have integral of the electric field. I'm going to drop the number notation since that's the only electric field we have. And so remember, this integral either becomes E times A or 0. So integral of the wall E dot dA just becomes E times the area of the wall of the cylinder. What is the surface area of the wall? So for a cylinder, if you think about unwrapping it, okay, if you think about unwrapping it, the area is going to equal length times width. Okay, what is the width of it? So the length is L. The width is just the circumference of the circle. So a 2 pi little r in this case. Okay, so the area will be E times 2 pi little r, L times 2 pi little r. Okay, the right side of the equation, Q enclosed, we need to deal with that. So Q enclosed is going to equal rho times the volume. Okay, we have to be careful with what volume we want. Okay, so the volume that I want is this volume, right? This is what actually has charge. So not the volume of my Gaussian cylinder. We just want the volume that actually contains charge. So we just want that volume right there. So that is the volume of a piece of the charged cylinder that has length So that length is L. Okay, that length is L, and it has the area would be pi big R squared. Okay. By the way, where did I get this? Again, rho is charge per volume. Okay. So if that's the case, then we have, so what is that volume? That's the volume of the piece of charge. Okay, so we have Q enclosed equals rho times the volume of a cylinder is the length times pi, and it's big R squared in this case. Okay, and so setting the left side equal to the right side, we have E times 2 pi RL equals rho L pi R squared divided by epsilon naught. Solving for electric field, we would have, if I divide 2 pi RL, the L's cancel, and so do the pi's. And so we're left with rho big R squared divided by 2r epsilon naught. And that's it for the electric field outside of that cylinder. Okay, so part B, we want to know the electric field when R is less than big R. Okay, so now we're going to pick a new Gaussian surface. Okay, I guess let me just redraw all of that stuff. So here's our charged cylinder. Really long charged cylinder, has radius of big R. Okay, so now we're going to pick a new Gaussian surface, and it's going to have a radius that is inside, or it's going to have a radius that's inside of this cylinder, still with length L. Okay, so here's the Gaussian surface that we'll pick. It has radius of little r, still has length of L. Okay, and we're going to apply Gauss's law to that. So closed integral E dot dA equals Q enclosed divided by epsilon naught. The left side will look exactly the same, E times 2 pi RL. Okay, dealing with the right side, how much charge do we want to count? We want to count just this charge in here, in that volume. Okay, so this time the volume that we want to look at is the volume of our Gaussian cylinder. So Q enclosed is going to be rho times the volume of our Gaussian cylinder, which is rho times, again, the volume is the length times pi, this time it's little r squared. Okay, setting the left side equal to the right side, we have E 2 pi RL equals rho L pi R squared divided by epsilon naught. This time the pi cancels that pi. One of those r's cancel one of those r's, and we're left with E. Oh, the L's cancel too. So we're left with E equals rho R over 2 epsilon naught. And that is the electric field inside of a uniformly distributed charged cylinder.